this set of notes is the first set of notes on the equilibrium unit. So it's just introducing the concepts of chemical equilibrium. So before we get started in talking about what equilibrium is, I'm going to talk about how chemical reactions occur. And so we have something that's called the collision theory of chemical reactions. And what this says is that when a reaction happens, what's really happening is two particles are hitting each other, and this might be like a molecule and a molecule, or an atom and an atom, or an atom and a molecule, something like that. They hit each other, and then they sort of like reach this weird intermediate transition state. And so I say that they kind of have this like Hollywood-style explosion where you get like molecules swirling around other molecules, or atoms swirling around other atoms, and they're exchanging electrons, and weird things are happening. And it reaches this thing called the transition state, where all sorts of things are sort of instably bonded to other things, and then it all comes apart, and there's new products in the end. And so that's kind of the idea. So you have a collision, all of the particles, all the atoms sort of swirl around each other, and new bonds get formed, other bonds get broken, things like that. And then in the end, you get this new substance. So that's a chemical reaction. And so the deal here is that transition state, that state in the middle when everything's sort of unstably bonded to one another, that is unstable, all right? Because you've got things that maybe are making more bonds than they would normally like to, or something that's making less bonds than it would normally like to, or electrons being transferred, things like that. And so it requires a certain amount of energy to get up to that sort of transition state. And so if the collision doesn't have enough energy, then the reaction isn't going to take place. So that's sort of the idea of the collision theory of chemical reactions. And also, I take a moment here to remind you that the word theory in science doesn't mean something that we just think might be true. The word theory in science actually has a really, really strong connotation. Scientists consider theories essentially to be like facts. And the difference between the word law and the word theory is that law is a description of something that's happened, and we use the word law when we're talking about something that we've observed over and over again, just describing what happens. A theory is an explanation that's based on repeated evidence that's repeated so often that scientists consider it to be like fact. And so the difference between theory and law isn't in how accepted they are. A law and a theory are both widely accepted by scientists. The idea of a scientific theory is that it explains things. And so this is a collision theory of chemical reactions, but it is what scientists regard to be the truth based on many, many observations of this. So that's collision theory. So in terms of making these reactions happen faster by this collision theory, there are a few ways that we can do that. If you increase the concentration, you're increasing how many particles are colliding with one another. And so if there are more particles, you're going to have more collisions, which means more of those collisions are going to be energetic enough to have the reaction occur. So it just makes sense that if you have more particles, then you're going to have more collisions there, and the reaction is going to go faster. Increasing the temperature has the effect of speeding up the particles, and if they're speeding up, they're going to hit each other harder, and if they're hitting each other harder, that means that there's a higher chance that they're going to have that necessary activation energy. That's what the E sub A stands for, activation energy, in order to create the products. And then this last way is by using a catalyst. In chemistry, what a catalyst actually does is it makes that transition state more stable, and so it lowers the necessary activation energy. And so it sort of just makes the reaction easier to occur. So we have this little map here for you. It's an energy diagram, and you see the two axes there. On the y-axis, we have energy, and on the x-axis, we essentially have time, but it's going from the products to the reactants. And so you can see here C represents the reactants, F represents the products. And so as we go through time, we go from the reactants to the products. You can see that energy spikes there in the middle. That spike is that unstable transition state, right? D here then would be the activation energy. So that's the difference in energy between where the reactants are and that transition state. It's called the activation energy. And then sort of once it gets up over that hill, it can fall down and become the products. And so it has to reach that transition state. What E here represents is the amount of energy that's needed if you have a catalyst. So this is kind of like the activation energy, but the activation energy when a catalyst is involved. So just going over a little bit of vocabulary here. Homogeneous, you're pretty familiar with that word hopefully from before, but if we're talking about if we're talking about equations rather than talking about things like solutions or mixtures, it has a bit of a different meaning. So homogeneous means the same, okay, but in this case it's talking about the same state of matter. So in this example we have a gas on both the product side and the reactant side, and so that would be a homogeneous reaction. Heterogeneous, on the other hand, there's different states of matter. So as an example here, we have a solid on the reactant side, and then we have a solid and a gas on the product side. And so those aren't all the same, and basically, if it's homogeneous, they're all the same. If it's heterogeneous, at least one is different than the others. So this one is heterogeneous. So I'm going to talk about a couple different examples that I have of equilibrium, just so that you can get this concept down. I think if you're trying to remember the concept of equilibrium, the one word that you should remember here is balance, because that's what equilibrium sort of means, is it's a balance between different processes. And you might be familiar with the word in terms of human beings. If you say that they don't have equilibrium, you mean actually that there's poor balance, and I mean like standing up. So like if you spin around in circles a whole bunch of times, you get dizzy and then your equilibrium is thrown off, so you've got poor balance and things like that. So some examples here that you might say in terms of two opposite processes occurring at the same rate would be like if you had a football game and they're kind of going back and forth and not really making any progress. So one team has the ball, let's say they make it 20 yards, the other team gets possession, they make it another 20 yards back the other way, the first team gets possession again, and they're just going back and forth. So their rates of the different processes are canceling each other out, and so you'd say that it's kind of at equilibrium here, it's kind of stuck in the middle. The example I like a little bit better here is this predator-prey example. And so many of you, when you were in biology, you probably did an activity with deer and wolves. And so I give this example where we've got, say, a wood that has deer and wolves in it. If you have more deer population, let's say that it's an especially rainy spring, you get lots of vegetation, the deer have more to eat, so the population of the deer goes up. Well, consequently, the population of the wolves would go up, and then there'd be more wolves to eat the deer, the wolves would eat the deer, the population of the deer would fall, then the population of wolves would fall, and then it would go back to normal. Now, if there was some sort of permanent disruption, like for some reason we were permanently getting more vegetation, well then we would be able to permanently sustain more deer and more wolves. But if it was just some sort of strange, weird accident that happened, that we have more vegetation one year than we do normally, then population of deer goes up, population of wolves go up, then population of deer goes down, then population of wolves go down. And it reaches back to that regular equilibrium that it's at before. So there's this balance that sort of brings us back to the normal population after some time because of these sort of opposing processes that are going against each other. So birth of deer versus death of deer and things like that. So specifically when we talk about chemical equilibrium, what we're talking about is the rates of the reaction. And so mostly we're talking about reversible reactions. Reversible reactions have this double arrow here. And so what's happening in a reversible reaction is it's something that goes both ways. And so a common example that I give is like freezing water versus melting water. That's sort of a physical change and not a chemical change, but it's a reversible process. Okay, if you freeze water, you can undo it by melting it. If you melt water or melt ice, you can undo it by freezing it. And so that's a reversible process. Similarly, we've got some chemical reactions that are shown here at the bottom. This one down here is a reaction between oxygen and ozone. So oxygen gas sort of spontaneously can become ozone, but it's not really favoring the products in this reaction. In fact, not much ozone is created at all from this O2 gas, but it does happen, and so there's a reversible equilibrium there between O2 and O3. So here's what's this is like a big deal. So lots of people, when they see the word equilibrium, they think equal concentrations of products and reactants. That is not the case. What it is the rates of production of the reactants and the rates of consumption of the reactants are the same, or the rate of production of the products and the rate of consumption of the products are the same. That's what's the same here. It's not that the products equal the reactants. So there's this concept down here at the bottom that you see. I gave it like a double star and an exclamation point. I want you to understand this concept of dynamic equilibrium. What this is saying, the word dynamic means that things are still changing. And so it's not like when you reach equilibrium, everything stops. So it's not like with that wolf and deer example that once you reach the equilibrium population of deer, that deer stop being born and deer stop dying and things like that. What's happening is the deer are getting born and the deer are dying all the time. And that's just like in chemistry. The reaction is always occurring in the forward direction and the reverse direction. So it's not like everything stops reacting when it reaches equilibrium. They're just the same rate, but in opposite directions. The opposite of this is something that's called static equilibrium. Static equilibrium happens when things stop moving, when equilibrium is achieved. And usually this is something that happens in physics. So if you've got like the forces balanced on something, everything will stop moving, and it's called static equilibrium. But for dynamic, change is still occurring. There's just no net change. And then we have this example here of a roller coaster ride. So on a roller coaster, it could be riding around, all day, and it's going up and it's going down, but it always comes back to the same point. It starts and then it takes off and then it comes back to the same point in the end. And so there's not a net change, but the roller coaster is still moving all the time. And so that's kind of like our dynamic equilibrium. I've got this example here of a situation where you've got a beaker and it's set on a hot plate, and I say it's like 90 degrees Celsius, so it's not quite boiling temperature, but it's certainly steaming temperature. In this case, we have a lid. In the other case, there's no lid. And so you see some different things happen here. On this one, steam is coming out, all right? And then because it's covered up, what happens is condensation will form on the lid. Many of you who have been cooking probably have seen this with pots. So it will be steaming, and then the condensation will come on the lid, and then it falls back down. And so this is an equilibrium situation because we've got steam coming out, and then it's recondensing, and it's coming back, and the general amount of the water stays the same. Over here in this one, there's no lid, and so as the steam is evaporating, it just leaves. And you might think over time here that eventually all that water is going to evaporate out of there, and then we'll just be left with this salt in the end. I kind of do a little bit of a review here on the solutions from last unit. So here, if we've got solid NaCl sitting in the bottom of a beaker, this is saturated. Here, this one also saturated. This one, everything kind of will stay the same, even though water is boiling away or evaporating away and recondensing. The concentration generally over time is staying the same. Here, as the water is leaving, the concentration of NaCl would be going up. But since it's at saturation already, what's going to be happening is the salt crystals are just going to come out of solution and keep piling on. And so you might have a larger mound of NaCl there in the end. All right, so of these, the one that's in equilibrium here is the first situation. It said, could equilibrium ever be achieved in an open system like what we have for beaker B? So in order for equilibrium to be achieved, the rate of a forward process has to equal the rate of the reverse process. And so the process here that would have to be counterbalanced is that water is leaving. And so I think you could get equilibrium achieved here, but you'd have to have some sort of process for adding the water back in that was leaving. Otherwise, it's not an equilibrium situation. So with chemical reactions, we kind of say that they all have their sort of happy place that they go. And what I mean by that is that if you start with all products, or if you start with all reactants, they're going to kind of end up at this same sort of stable place in the end. And so if you have lots of reactants, that means that a lot of those reactant particles are going to be hitting each other, and it's going to be going, and they're going to be forming more products and be using up the reactants, and they'll get to some place where it's nice and stable. However, if you started with all products, those product particles are going to be flying around, and you're going to have them hitting each other, and they're going to make reactants in the reverse reaction. And so what happens is, regardless of where you start, you sort of end up at the same equilibrium point. And so it's kind of important to understand that about equilibrium. You don't actually have to have the same starting conditions. It will always proceed that sort of way. Alrighty, so we're going to talk about something called the equilibrium constant. And what that is it's a way that scientists came up with for quantifying equilibrium. And it relates to how much products there are versus how much reactants at equilibrium. And so what we do is we take the number of products and we divide it by the number of reactants, and you'll kind of see how that goes. In this, we don't use solids and liquids because solids and liquids don't kind of spread out when they're mixed together all the time. So we use gases and aqueous substances only in the KEQ equations. The equilibrium is going to shift depending on temperature. I'll talk about that more when I talk about Le Chatelier's principle. There's an entire PowerPoint on that later on. And then this last thing is KEQ doesn't tell you anything about the speed. So you could have a reaction that favors the products, that's going to make a lot of products in the end, but it might take millions of years for that to happen. And so keep in mind that this KEQ tells you what's favor the products, the reactants, but it doesn't tell you how fast the reaction is going to happen. And so it could be a very, very long time before equilibrium is actually achieved. So in a given chemical reaction, the lowercase letters here you can see represent the coefficients, the numbers that are out front of the substances, and the capitals are the substances themselves. And so when you write the KEQ, it's products over reactants. And so all of these numbers that were out front, these coefficients, hopped up here, and they became the exponents when we write it in the equation. And so products go on top, reactants go on the bottom. So we have the concentration. That's what the brackets mean, by the way. The bracket means concentration. So concentration of C particles to the C power, because this coefficient, lowercase c, ends up going up here, and then capital D to lowercase d power. That's kind of how it works. And as I go through some examples of that, I think it will make a little bit more sense. So here's an example of a reaction and the KEQ that goes along with it. To help you understand why things are squared, I've written this reaction out kind of separately. So instead of saying 2H2, I said H2 plus H2. So we got H2 plus H2 plus O2 yields H2O plus H2O. And the reason I do this is because the rates of the reaction are dependent on the particles colliding with each other. And in this case, hydrogen is going to be twice as influential as oxygen because you need two hydrogens for every reaction. H2O also, in terms of the reverse reaction, H2O is going to be twice as important in terms of determining the rate of the forward reaction as oxygen is, the reverse reaction, whereas oxygen is, there's only one of them, so it's going to be half as effective in determining the forward reaction. So going through here, this is how we write it out. So H2O has a coefficient of 2, so that becomes this exponent here. We've got H2 has a coefficient of 2, that becomes this exponent, and this is a 1 here, so it becomes a 1 here. This reaction is reversible, you know that because of the double arrow, and it's homogeneous because all of them are gases. So just kind of testing you on identifying those sorts of things. Make sure you're still remembering those. So this equation is balanced. You got to make sure it's balanced for writing the KEQ. It's reversible and it's homogeneous. At this point, if you want to stop the video and try and write the KEQ equation, that would be good. I'm going to go through it here in just a second, but if you want to pause the video and try it on your own, that would be good at this point. All right, so this one, it's products over reactants always, so it's concentration of CO2, and it's squared because there's a 2 here. So the 2 as the coefficient becomes the power. Then we have it over the reactants. 2 in front of the carbon monoxide, so we've got a 2 here, there's a 1 here, and so it's a 1. And so that's how that would go. All right, for this one, very similar again. It's balanced, it's reversible, it's homogeneous. Go ahead, pause the video, try to figure out what the KEQ equation would be for this, and then I'll go ahead and show you. So here it is. We've got NO to the 4th, because it's products over reactants again. Coefficient of 4 becomes exponent of 4, concentration of H2O to the 6th, over concentration of NH3 to the 4th, concentration of O2 to the 5th. All right, so that's how you write that. So I'm going to talk here about KEQ and what it means. So if you get a KEQ equal to 1, that means the products are relatively equal to the reactants, because if you think about how you calculate it, it's products over reactants. So it'd be something like 2 over 2 here, and you get 1 in the end. So the relative amount of products and reactants are pretty similar there, and so we're going to get something like 1. All right. We say here that the equilibrium lies in the middle. What that means is if you write out a chemical equation, the reactants are on the left, the products are on the right. So if the equilibrium lies to the left, that means there are more reactants. If the equilibrium lies to the right, that means there are more products. This one is in the middle because there are about an equal number of products and reactants. We say it's about half complete. If you started with just reactants at the beginning, you'd go about halfway to completion. All right, and so there's a significant amount here of both reactants and products when you get to equilibrium. Another case here, if we've got KEQ and it's larger than 1, in fact, this is much, much larger, then it's going to be product favored. The reason is because if it's a large number, then there's going to be more, like a larger numerator, smaller denominator. Okay, for example, if we had like 10 and 1, you'd get this number 10 out of here. 10 is more than 1. Okay, so we've got this situation where product favored here in this case. We say the equilibrium lies to the right. If you started out with just reactants, it would go mostly to completion. So that's how that one works. The other example here is if KEQ is less than 1. And here it can't be negative. So really what we're just talking about is decimal. So if KEQ is a decimal, then we know that it is reactant favored. All right, it's because the reactants are going to be the big thing. If you have a small thing divided by a big thing, you get a decimal. All right, so we say the equilibrium lies to the left because that's the side of the chemical equation where we have the reactants. Okay. And yeah, so if you started with just reactants, almost nothing would happen here, and we say the reactants are favored. Okay, so that is it. If you want some practice plugging some actual numbers into these equations, there's a worksheet on the equilibrium constant, so that's where you'll get that practice. So find that, do practice at plugging these in, and watch that video as well.